Alan Turing was a very playful man, and if you look at the kind of work he was interested in, he was not just decrypting the German codes, but he also did things like work on biological pattern formation. So he produced an explanation as to how the leopard got its spots. I don't know currently the status of whether or not that actually is how the leopard got its spots, but it actually does work for a lot of other biological systems. So he was a man interested in the formation and creation of patterns and also, of course, their parallel destruction. So I'm going to talk today about the data science of play. Data science allows us to understand human behavior at a resolution and a scale that I think we've never been able to have before. Right? We're able to follow individuals throughout the course of a day or even in some cases a lifetime, and we're able to follow many of them together as they interact with each other. And as life gets easier, right, as it's easier and easier to feed ourselves, as it's easier and easier to meet our basic essential needs, my claim is that over time, more and more of our behavior will be not directed towards the satisfaction of goals, but to something else altogether. And under that something else, I call it play. So here's a definition of play, right? Human behavior in the absence of a goal. Okay, and we'll try to unfold this a little bit. In fact, many of us are lucky enough that we get paid essentially to play, right? If we're scientists, if we're artists, if we're writers, most of what we do is not directed towards the immediate satisfaction of a need. Play is deeply connected to part of the scientific process. I think as scientists, if you're a scientist, you understand yourself to be playing. And so one way to see this, right, is why it's so painful to write grant applications. Right? Because grant applications, like, you have to pretend that what you're doing has this immediate purpose, right? It's incredibly painful to say, okay, we're going to investigate X because X will allow us to satisfy, national needs Y and Z. And what I think we'd really like to say, if we were honest about why we needed the money to do what we wanted to do, we would give an answer somewhat like the Star Trek answer. And there's no, I think it's not an accident, right, that Star Trek, a vision of the future, is also a vision of where people take, very expensive instruments like the Starship Enterprise and go out. And what do, right? To explore strange new worlds, to seek new life and new civilizations, to boldly go where no one has gone before, right? So, in a sense, we would like to live in this world. We think, to a certain extent, that we may even be close to living in that world. In fact, if you look at sort of the history of our understanding of play, people have been living in this world already. So most famously, children, at least children who have a certain basic set of needs met, children play, and we consider that play to be fundamental to their education and their growth. So here's John Dewey. He's a philosopher of education. He worked at the laboratory school at the University of Chicago. He defines play as an attitude of freedom, free from subordination to an end imposed by an external necessity. So that's Dewey. There's play also in the non-human animals. This is a ethologist, Gordon Burkhardt. He talks about play as demonstrated in the animals when they encounter what he calls the relaxed field. The animal is not strongly motivated to perform other behaviors. He's not starving, preoccupied with mating, setting up territories, or competing for resources, right? So children play and animals play. But play, behavior, complex behavior in the absence of a goal, is something that has been accessible to some fraction of the population since basically the beginning of recorded history. So this is Aristotle, who talks about the proper activities of a gentleman, whatever that means, right? And for Aristotle, right, what you ought to be doing is the useless, right? You ought to be sitting around and doing activities not for a need they will meet, but for the very sake of those activities themselves. And he talks about the playing of music as a canonical activity, not just an example of play, but in fact the highest good for a human being. Okay, so these are sort of abstract definitions, right? So here are a few examples. This is sort of the timescales of play from seconds up to centuries, right? So playful activities that you might engage in, right? The appreciation of complex artworks, dressing, getting dressed in the morning, right? Like the temperature in this room is like pretty amenable to human survival, right? So you're able to wear, sorry, are you cold? I would give you something, but I don't have anything to give you. I should say, by the way, please feel free to ask questions. So I have a 45-minute version and an hour version. So if you don't ask questions, unfortunately, you get the hour-long version. Dressing in the morning, most of us can meet our needs for sort of decorous dress and keeping warm or keeping cool pretty instantly, and we spend most of the rest of our time dressing, choosing what to wear without any particular aim in mind. We don't dress directly to seduce, we don't dress directly to impress, but we put on clothes in a way that seems somehow playful. Greeting and leave-taking, when you say hello to your friends, you say goodbye to your friends. Oftentimes what you do is you don't just simply acknowledge their existence, but you say something, you engage in some kind of relationship with them. Like every evening I have to turn in my little card that lets me into the Turing Institute, and I make a brief conversation with the person there. Okay. Sort of on longer timescales, or perhaps more formally, like jazz improvisation, dancing, when you dance with somebody. Right? Improv comedy. One sign, by the way, of example of play is if the goals themselves become too apparent, the playfulness disappears, right? If you're dancing with somebody and it becomes overtly the sort of, maybe the sexual aspect of the dance becomes too overt, then all of a sudden you're no longer dancing, you're doing something else, right? Improv comedy, if you've ever seen this, right? Religious activities are often forms of play. Dinner party conversations, right? You don't go to a dinner party to eat. Right? You go to a dinner party to talk with your friends. And of course, if you go to a dinner, I did this once, you go to a dinner party and someone says, okay, the topic of conversation is X and we're going to solve this by the end of the dinner party. This is a disastrous dinner party. We have a sense of what it means to have a good dinner party, in other words. And that sense you have is a theory of play in that particular environment. What in the States we call a college bowl session, where you stay up for hours and hours, right, with your friends at university, and you talk, and you're not actually getting better grades because you're talking, you're doing something else. Right? If anyone plays D&D, that's a form of play. Right? And so now we're going to longer time scales, right? So the production, not just the appreciation of artworks, right? What's the point of appreciating art? I mean, if you go to the museum and you look at a piece of art, what's the point? You're not learning any bit of information. It's not like the map of the tube, right? But also the production of those artworks itself, intimate human relationships, scientific experimentation, speculation, collaborative online projects, right? People go on the internet. It's not quite clear why they go on the internet and talk so much. Right? Often pseudonymously, right? They have no real, like they're not producing anything for themselves in the real world. Why exactly are they doing that, right? Okay. And then on even longer time scales yet, right? And the life of an artist, the life of an intellectual, what people sometimes refer to as their hobbies are often decades-long forms of play. And then play itself extends well beyond the human lifespan to like basic features of civilization, the things that we do that make our culture sort of worth protecting, right? The reason we eat, in some sense, is to do mathematics, to write poetry, to do philosophy, right? The tea ceremony is, by the way, a great example of a centuries-long, somewhat religious process of continuous evolution. Okay. So we're experts, I think. So we understand these as activities. We understand these as valuable activities. We actually have very little notion of how to describe them or explain them. We have no good mathematical theory of play. We have a great theory of goal-dominated behavior. I'm a professor, supposedly, of social and decision sciences. So this is how I teach my students, right, how to predict and explain human behavior. Okay, there's two things, right, like what the person knows, what you know, and what you want, okay? What you know, you describe. I teach my students how to do Bayesian reasoning, how to manipulate states of belief according to the theories of probability, right? We can describe what people want using utility theory, right? If I combine these two together, I know what you're going to do. At least this is the account we have. It's the basis of things like game theory, right, of rational choice, okay? Play, of course, doesn't fit under this framework. In fact, it may be better described like this. What you know is, in fact, driving what you want, right? And together, these two things combine to form what you do, right? And of course, okay, there may be some kind of external forcing on what you want, right? No play is totally pure, right? We go to the museum not just to look at beautiful art, but maybe to signal we're the kind of people who go to the museum to perceive beautiful art, right? No form of play is entirely pure, right? But making what you want derivative of what you know, making your epistemic states something that drives your desires, makes the standard rational choice framework completely fall apart. So I don't know if you've bought my account of play here. I will give you, okay, if you just can't imagine what it would mean to act in the absence of goals, right? Some people, there's this sort of like kind of undergraduate fallacy where, you know, we're always maximizing our utility, right? Whatever I do is like, oh, you're doing that because that's exactly what you wanted to do. Now, of course, that's not a predictive theory, right? Because it's something that only works post hoc, right? But it's easy to fall into. Just if you can't imagine people sort of doing something for a reason other than satisfying a desire, here's a separate definition. This is the working definition of play. I go to the canonical comic XKCD. Do people read XKCD at all? Yes, okay. So this is just one of the many, I mean, Randall Moreau understands things better than many scientists. He is himself, in some sense, a scientist. And this is a great interaction here between this chess player and this sort of, kind of douchey guy who thinks he knows everything about chess, right? So he's watching a chess player. It's like, look, like chess is really simple, right? You want to capture the person's king, right? So you should be like moving all your pieces towards the king, right? That's the theory of chess, right? And of course, right, that's not actually what chess looks like, okay? So even games with fixed rule structures where the goals are made completely apparent, right? In some sense, the goal of chess is to capture the king, right? But what makes chess playful, I would say, is the following, right? This is sort of a warning sign of play, right? Where the goals are too simple, right, compared to the complexity of the behavior. When goals are incommensurate, right? When things are so like, yeah, like what's the rule of Go? Like just capture more area than the other person. Like that's really simple, right? But if you look at what happens when you set up those rules, people behave in ways that are sufficiently complex that all of a sudden you're no longer in this simple framework where you can explain actions by reference to a future goal. Okay. So what am I going to do in this talk? I'm going to tell you how I intend to quantify play-like behavior, and not in children. The opening slide was from Alison Gopnik's lab. Alison Gopnik studies actual children playing in an environment trying to solve puzzles in a playful kind of way. It's a wonderful thing. They don't let me do that, right? So I have to go look at human play in archives, right? We have records of how people play. So I'll tell you a little bit of how we quantify that behavior, and then I go through a couple case studies that we've done. I'll talk a little bit about how string theorists play, how people studying in physics, right, in this sort of realm of physics that's so divorced from actual application to the real world, right, that in some sense the problems they're solving are not being driven by immediate needs to make, I don't know, like make the superconductor work at higher temperatures, okay? And I'll talk about something we call the Calvinball problem. If people know Calvin and Hobbes, that's coming, right? I'll talk about lyric poetry, another form of play, right? Lyric poetry is clearly, I mean, in some sense, it's overtly designed to speak to a beloved. Actually, that never really happens. Okay, it's doing something else altogether. And finally, I'm going to talk a little bit about the role of conflict and argument in play. Right? If you remember when you were a child and you played with your friends, the chances are you often got into conflicts with your friends. Maybe about the rules of the game, whether they were playing correctly or not. Sometimes those conflicts, like, maybe ruined friendships, but oftentimes those conflicts can enhance friendships as well and can enhance the practice of play. And so the final example will be of sort of, one of these Star Trek-like projects, right, to catalog all the world's knowledge, and some it's very unclear what they're meant to be doing there. We'll talk a little bit about the role of argument and conflict in play. Okay, so how do we quantify play? Well, what we're going to do is attempt to reverse engineer the structure of the human mind, okay? So we'll solve one problem by trying to solve an even harder problem. In particular, what we're going to do is I'm going to introduce just briefly a mathematical model for human cognition, for thinking. The problem of thinking, right, is that thinking is two things, right? Thinking is what we do and what we aspire to do, right? So a student who makes lots of errors is thinking, but also not thinking, right? And one way I do this is just a little painting of the Annunciation, right? On the one hand, you have sort of like kind of normal, fallen, this is Mother Mary, right? Fallen human reason, right? And on the other hand, you have this idea that reason could be perfect. So what's strange, in fact, is that while we have no idea how ordinary people reason, we have no idea how that works, right? You put people into a lab, and I mean, if you look, for example, this is the field called behavioral economics. Even when people are trying to satisfy their needs, they behave in totally bizarre ways that we haven't been able to model. If you look at the list in behavioral economics of different fallacies that people exhibit, half the fallacies contradict the other half, right? So sometimes you're biased towards things that are common, and sometimes you're biased towards things that are rare, and no one can really disentangle it. So it says that we have no idea how people think, and we're working it out, but we certainly are nowhere near producing a mathematical model of it. Bizarrely, actually, we do have a complete theory of optimal thought. And that's Bayesian reasoning, right? So Bayesian reasoning, okay, we've had a theory of optimal thought when everything is true or false, deductive logic. We've had that since Aristotle, who you saw before in his theory of play. He also had a theory of logic, which turns out to be correct, right? So deductive logic allows you to take a statement like this, A is true and B is true, and transform it into all of its versions that are equally true, right? A is true and B is true implies that it's not the case that, A is false or B is false, right? So we know how to take statements that are true and transform them into other statements that are true and vice versa, right? So we have an optimal theory of deduction. We tend not to deal with statements that are certain, entirely certain, right? Most of our knowledge in the world is entirely fallible. And so this is the kind of reasoning we tend to do, right? It's inductive, right? We reason that most birds can fly, and therefore this bird in front of me can probably fly. So it took us a bit longer to work out the correct mathematics to describe moving from a statement like this to a statement like that, but we were able to do it. I learned it from this guy, E.T. Jaynes. He's a physicist. Okay? But this goes back to the Reverend Bayes and many people sort of in the Enlightenment who were trying to work out how to describe the manipulation of statements that are not entirely true nor entirely false statements about the probability of something happening. Okay? So E.T. Jaynes, he's a great man, right? The joke is he looks like he's going to beat you up. He's like a bruiser. Jaynes, actually, he wrote a wonderful book called Probability, the Logic of Science. And for Jaynes, this was everything. Once you knew how to do this kind of stuff, how to talk about the optimal manipulation of statements of things that may or may not be true, right? Okay. Once you solved that, for him, you solved everything. I don't think that's entirely true. Okay. But this is a very good framework for trying to model human behavior. Okay. In some sense, what we do is we take this angel here as an upper bound for the behavior of an ordinary person. The angel, okay, we're going to model the angel's perception, let's say, of a social environment. We're going to give that angel sort of infinite computational capacities, practically meaning I'll just run everything on a laptop and imagine that that person is making those decisions that fast. And so by modeling this perception by the optimal version, we at least get some upper bound on what's going on. We can talk about things that a perceiver might see in their environment. We can talk about things the perceiver might expect or might believe. Okay? It's not perfect, right? But it's the best we can do. And in fact, this is something, I don't know if Rob's here, this is a style of modeling human behavior that goes back to a number of people, including Nick Chater at Warwick. So there's a wonderful tradition of doing this, in some sense, short-circuiting psychology by going straight to the mathematics. But it's important to remember that, in fact, of course, we're not optimal agents. We can't manipulate these statements perfectly. We often make mistakes. The way in which we deviate from perfection is something we have yet to learn how to model. Please solve it and let me know. All right, so I'm going to teach you one little thing, right, about how Bayesian reasoning works. Okay? What it does is it models statements about the world probabilistically. And what that means is, like, let's say the world can be in like 10 possible states. Right? It could be raining, or like it's Britain, right? So raining in like 6 different ways, right? And there's like one form of sun that's very rare, right? So you have some belief about the rain, okay? And let's say you say, okay, look, it's maybe very likely it's raining outside if we were to raise these shutters. And you might say, okay, 0.8, 80% chance of rain. Okay. So what you do continuously when you model, okay, optimal reasoning is you attach probabilities to statements. And I'll tell you one aspect of how we manipulate those probabilities, and that comes from information theory. I'll tell you in particular how we model the uncertainty of an agent's environment. So they believe that a certain set of things could be true. They attach probabilities to those things being true. And we would like to sort of quantify the extent to which they're uncertain about the state of the world. Now, it is either raining or not raining outside, right? So if I were to go and sort of, open the window and look, I would know with absolute certainty, modulo my, I might be on drugs or something, right? But just, I'd know with very high probability whether or not it was raining outside. Right now, I don't have a good notion, and I'm somewhat uncertain. So how do we quantify that? One way to think about is quantifying this using a game called 20 Questions. Who here is a computer scientist? Can you raise your hands? Okay, good. So I'll ask you guys, right? 20 Questions is a game that you play often with children, like on long car rides, okay? But one way to think about it is a game that tells you how uncertain you are about something else in the world. So in the game of 20 Questions, right, there's like 2 players, right? There's the parent and there's the child. The parent thinks of something, and the child asks questions in order to elicit what the parent is thinking of, right? And the parent can answer only yes or no, okay? So, I don't know. Josh, Matt, would you play 20 Questions with me? You guys know 20 Questions, right? Okay, so okay, I'm thinking of something, right? And they're going to play 20 questions. So they're going to ask me questions, yes/no questions, designed in order to. Oh, we're going to get this on record too. Designed to figure out what it is I have in mind. And I'll just, I'm thinking, let's say, of a noun. I have some noun in mind. Okay, so I got it. Okay, go for it.
Is it alive?
Yes.
Is it a mammal?
Yes.
Is it smaller than a human?
No.
Is it an elephant?
Yes. No one's ever gotten that before. People have got, well done. Okay, well done. So 20 Questions is a great game. It's a great game. No, it's rare. I mean, usually it takes longer. So in the game, so I mean, and I'll just tell this quickly, right? So yeah, sorry, question.
Don't think of an elephant.
I know, right? Okay, this is the book that came out in the States on how to program people to vote for the Democrats. So the game of this famously, and this is a fun joke that's it's worth telling, right? So this was also a game in communist Poland, a game show in communist Poland on television, and so they would invite like members of the plumbers union to come, and they would play 20 questions on television, live television, and broadcast it to the people of Poland. And so that was fun, I guess. And the game had to be canceled when the Polish Mathematicians Union was invited to play this game. And this is, I mean, I can't find it on Wikipedia, so it may or may not be true. But here's how they, of course, played the game, right? They said, OK, is the word, thank you, Carmen, right? Is the word that you're thinking of, does it fall in the first half of the alphabet or the second half of the alphabet? OK, first half, right? Does the word fall in the first half of the first half or the second half of the first half, right? And by a series of just binary splits, you can get this game over as quickly as possible, right? So what I want you to imagine is, how do you finish this game as quickly as possible? Right? And in fact, you know, because like there are more words on this, you know, in the first couple volumes than in the second couple volumes, right? So maybe there's a more efficient way to ask this, right? So here's an idea, right? Let's imagine the optimal script. I'll give you a simple example. You're playing this game against your dad. He only thinks of 3 possible things, okay? These are the chances that he's thinking of each of these things. So these are your Bayesian. This is your Bayesian prior of what he's thinking. So if you want to get this game over as soon as possible, which question do you begin with? Or give me a question that you might begin with. Well done, Chico. Yes, right? Because half the time, the game is over, right? The other half the time, no. OK, now you have to split, and now you actually have 2 equivalent questions, bird versus tree, right? So, and this turns out, in fact, well done, to be the optimal script, right? So on average, right, if you play this game with the optimal script, the game is over in 1.5 questions. So what is amazing, we did not learn this from Alan Turing. We learned this from Claude Shannon. I understand that they almost met. Or maybe they met and they weren't allowed to talk about what they were doing because, of course, it was top secret at the time. So you may know that you can compute the average depth of this tree without actually constructing the tree, okay? With this formula here. The physicists call this entropy, right? So if I just know the probability of each of the options, I can tell you how many yes-no questions on average I need to ask if I remember that optimal question asker, like Chico, right? If I'm that optimal Bayesian angel, how quickly can the game get over? Okay? So this tells me how uncertain I am about my environment. Here's an example. I love playing with real-world text, right? So this is Jane Austen's Pride and Prejudice, right? So let's imagine, right, that I stick my hand into Pride and Prejudice and I take out a word at random, okay? How many yes-no questions on average will it take me, or will it take you, sorry, if you're optimal, to figure out what that word is? How many yes-no questions on average? People want to guess. Is it 100 questions? 15, okay. Close, right? If you imagine, let's say, imagine splitting that tree, right? So that each word, right, was equally likely. You put it at the bottom, right? With 15 questions, you could do what? It's about, 2 to the 10 times 2 to the 5. Thank you, Taha. Bayesian angel, right? So 32,000, it's actually a little bit more than the vocabulary of a normal human being, even Shakespeare. Well, Shakespeare's 40,000. So, and that's, of course, if they were to use all these words uniformly. It turns out, in fact, that the average number of yes-no questions, aka the entropy, is 9.06 bits, right? And bit is the unit of yes-no questions, right? Binary digit, right? So on average, it takes 9 yes-no questions. Now, if you think about that for a second, that's a little crazy, right? Because if you actually, right, had a balanced tree, right? So each time, right, you split, right, uniformly, with 9 yes-no questions, right, so 2 to the power of 9, right, the first question splits 2, then 4, then 8, 16, 32, 64, 128, 256, 512, right? So if that tree is balanced, you're splitting uniformly. At the bottom, you can only refer to 512 words, okay, which is the vocabulary of Dr. Seuss. So clearly, something funny is going on here, right? And in fact, I can tell you exactly what's going on. Let's look at a sentence from Jane Austen. So this is the first sentence of Pride and Prejudice. It is a truth universally acknowledged that a single man in possession of a good fortune must be in want of a wife. If you look at this sentence, right, most of it's actually kind of junk, right? It is that in of must be in want of right? All of the sort of elaborate words, okay, the rare ones, right, are interspersed with these really common ones. So if you're imagining constructing that tree, one of the first things you might ask is like, look, is it one of those junky words? Yes. Okay. Is it the? Okay, yes. Right? So the game's over in 2 questions, right? So the tree is a really unbalanced tree, right? So 9.06 bits, right, is only a partial representation of what's going on here, right? That's why sort of on average, yeah, it's over in 9 questions, but really the variance is high. And by the way, no one's actually written on this. This is a freebie paper. Work out the variance on the number of questions. And that turns out to be a really interesting problem. So here's a little fun feature, right? So this is, that's Jane, right? This is Pride and Prejudice. 9.06 bits, yes, no questions. Here's another example from British literature. This is Virginia Woolf's To the Lighthouse, okay? Very different kind of text. How many yes, no questions on average do you need to work out, you know, if I stick my hand to the lighthouse, what word is hiding in there? Higher or lower? God, you're killing me. It turns out indeed to be the same within error. Okay, so there's when I measure 9.13, okay, technically it's higher, but in fact we do a little bootstrap to figure out what the errors really should be. So in fact, even though the vocabularies are entirely different, right? As you know, Virginia Woolf has the word like X-ray that does not appear in Jane Austen, right? But in order to get X-ray in there, right, she has to throw out like one of those words, like referring to the special kind of carriage that people drive, right? So there's some kind of flux there of things getting yanked out or put back in. Okay, so this is the study of uncertainty. This is the entropy or the information or the uncertainty of the system that you measure with this p log p, right, the average number of yes/no questions. That's part of how we'll characterize the expectations of an audience given a particular behavior. Okay, so I need one more thing. Here's your optimal script for your father, right? You've learned what your dad is like. Right? After playing this game a lot of times, you kind of figure out, okay, it's tree, bird, or car, and these are the probabilities. And once you know that, then you build this optimal script here. But let's imagine that you train on your father, right? You've trained on your father. You have this optimal script, but you encounter your mother, right? So your mother's like your father, okay, except she has slightly different probabilities, right? So your father is biased towards cars, like he's like an Uber driver. Your mother, right, she's biased towards trees. She's a theoretical ecologist, okay? So now, notice that her uncertainty, the entropy of this distribution is the same as your father, but if you use your father's script on your mother, it's no longer going to be efficient. Because you'll split on car first and not tree, and now this is no longer the right, sort of the correct question to ask, right? And so instead of the game being over in 1.5 questions, it's actually over in 1.75 questions. You're inefficient, your coding is inefficient, right, at 1/4 of a bit. Fantastically, we can also figure this out without building the trees. Does anyone know what this is called if you're a computer scientist? Kullback-Leibler Divergence. Okay? So Kullback-Leibler Divergence says, okay, look, I have some probability distribution, Q, that I've learned. I build an optimal script for it. Right? I build an optimal sort of yes-no question script. But in fact, I encounter this probability distribution, P. How many extra questions, right? What's my coding inefficiency because I encounter P instead of Q? This quantity turns out to predict an enormous amount of human behavior, surprisingly large amount of human behavior. Here's an example just from the visual system, right? In some sense, Kullback-Leibler divergence allows you to say, look, I have this pattern, pattern A, right? To what extent does somebody who believes in pattern A, who's encountered pattern A, to what extent are they surprised, are their expectations frustrated by encountering pattern B? So here's just one example from a study of how people look at videos, right? So just take this first line here, right? So you get these people in a lab and you have them watch a video of like kids playing soccer, right? So what I can show you is I can show you the uncertainty of each patch of the video, right? So I'll take a little patch of the video screen, right? And wait 5 seconds and look at the distribution of pixel values in that little patch, right? So I build up a probability distribution, and then I can measure the uncertainty, right? So this is sort of a heat map of where the uncertainty is, right? So you look here, down here is the grass, right? The grass is like either in shade or in light, and so like sometimes it's green and sometimes it's black, right? So there's kind of a lot of uncertainty there. You can see it's really high uncertainty. But now what you can do is also measure the Kullback-Leibler divergence, which is sometimes called Bayesian surprise, or just surprise, right? What this does is say, okay, look, I've learned the probability distribution in 5 seconds. Now I'll go to the next 5 seconds and measure the probability distribution again. What's the Kullback-Leibler divergence between those two? To what extent am I surprised if I train on this but encounter this? And now, in fact, the grass is really boring. Because yeah, it's like green or it's black, but like it's pretty much green or black the whole time, right? It's flipping back and forth, but that's not surprising. What's really interesting is somewhere up here where all these kids are sort of fighting over the ball, right? That's where the surprise is really high. And then, in fact, of course, you can actually take an eye tracker and look where people attend to. And in fact, the human eye is drawn to those regions. We're drawn not to the regions that are really diverse and bumpy. We're drawn to the regions that frustrate our expectations, at least at a very low level in the visual system. If people are interested, so we just had a big meeting here on the Cognitive Science Conference held in London this year. And so a great sort of, like, you can take this kind of work really far. You can match it to physics, and physics is called free energy. There's something called predictive coding. So if you go to the papers by Carl Friston and the derivatives, you'll find a huge amount of literature on this particular phenomenon. It's kind of a lovely thing, right? At least at the low levels of our visual system, we are like really good scientists, right? We're always trying to, like, we're building theories. We're like Popperian scientists, Karl Popper, right? We're always going out there and trying to, like, trick our, find the things where we're tricked. We're always trying to look at the things that violate our expectations. All right. So what have I taught you so far, right? I've taught you, okay, I've talked about play. I said we want to understand play, right? I've taught you how to model human behavior in terms of the learning of patterns and the attention to phenomena that violate our expectations, right? Clash of patterns, okay? And so now what I'm going to do is I'm going to apply just this simple equation to study some slightly more advanced, evolutionarily advanced forms of behavior, right? So this is like really low level. This, like, lizards presumably will do this too, right? But lizards do not do mathematics. That's what I'll talk about now. Mathematics is a lovely example of play, right? There was actually a great sociological paper written by a French sociologist where he went and sort of interviewed mathematicians, Bernard Zarka. Zarka was really interested in the sort of class structure of mathematics in France. So it turns out, like, the applied mathematicians tend to come from working class families. The pure mathematicians tend to come from, like, extremely wealthy families. But among the pure mathematicians, 62% of them describe what they do for a living, right, the meaningful aspect of their lives, as a very pleasurable sort of game with the appeal of the unknown. Okay? So mathematics is in some sense a game that people play with each other. It's like this centuries-long game of chess, right? There are some rules. The rules themselves are under evolution. I got some of this from this book here, I should say, Michael Harris, who's a mathematician at Columbia and then sometimes at the Institute for Advanced Study. Itself formed as an environment. This is in Princeton, New Jersey, and sometimes formed as an environment people could play, right? A little bit like how we build things here, or maybe like the Alan Turing Institute. Here's just an example of, like, in case you're not convinced that mathematics is totally useless. Do people know the Banach-Tarski paradox? Right? Banach-Tarski paradox says, like, okay, I mean, here's the formal statement. It means, like, I can take an orange and with, actually, it turns out 5 cuts, right? If I cut the peel of the orange, right, into 5 pieces in a certain special way, then I can reassemble the pieces into 2 oranges of equal size. This is, in some sense, totally useless knowledge because it's obviously not true, right? But according to the rules of the game, of course, the cuts have some very bizarre properties to them. So somehow a paradox like this, not a paradox, actually a theorem of mathematics, right? Somehow these theorems are being created as part of a game that has some disconnection from reality, right? So let's understand that, okay? What I did here is I took papers from the High Energy Physics archive. That's where string theorists place their articles. String theory is not exactly mathematics. It's close enough. And string theorists are more organized than mathematicians, so they tend to put all of their articles in the same place. I also happen to have a past in physics, so it was easier for me to read these and understand, like, occasionally get some crank articles. We'll talk a little bit about that if you like, right? But it was easier for me to handle this, right? But string theory forms like a similar kind of world, right, where people are writing articles, but in some sense they're not particularly being challenged by the data, right? They're writing articles in response to other articles. They're making moves in response to the moves of others. This has, of course, been criticized. So there's a number of books that have come out, one by Lee Smolin, The Trouble with Physics, another one by Roger Penrose, both suggesting that somehow the disconnection of physics from reality has been a bad thing, but let's just take it as a given. Okay? So we're going to apply Kullback-Leibler divergence to understand this archive. Okay, we'll take an article, right? Make a bag of words model. There's actually many different ways to model an article. This is a problem of NLP, right? How do I describe in a Bayesian fashion the context of a text? I'm just going to take a bag of words. So I'm going to say basically the same thing we did with Jane Austen, Virginia Woolf. For each article, I'm going to say what's the probability of the different words appearing. So that's PI, the probability of word I. And then I'm going to say, look, I'm going to compare that article, right, the contents of that article, to the stuff that's come before. And I'm going to do that by taking all the stuff that's come before, turning that into a probability distribution, and then using simply Kullback-Leibler divergence to tell you the extent to which a new article either confirms or violates the expectations you might have formed about the field given the articles that have come before. So this is our first bit of data science on play, in this case in string theory, right? So in case it's not entirely clear, right, I have two distributions, right? And in this case, we'll do it on the scale time of a month. So here's a paper from this month. These are all the papers for the distribution of words and all the papers from the previous month, okay? And we're just going to compute that quantity and show you over time. So here it is from 1992 to 2004, which is the range of the data that I had. And the first thing you can see is like, okay, like the level of surprise month to month in physics is pretty constant, right? So from 1992 to 2004, you write an article like there's some, it's not zero, right? Your article is going to violate the expectations formed in what's come before, just in part because you're not copying these things directly. But it's actually sort of almost like, on these short timescales, sort of like Brownian motion, like people are kind of bumping around. If you look on slightly longer timescales, you start to see some interesting phenomena. So here's an example, right? So the black line was surprise from one month to the next, okay? But this green line here, this is the surprise from 1 month to 3 years, so the month 3 years previous. Okay? And what you can see here is, in fact, the surprise was higher earlier and is now actually declining. And so what that means, in other words, is that in 1996, for example, people were deviating from the past more strongly than they are today, right? This point here is lower than these points here, right? You go down in time. And in fact, one way to talk about this is there's some kind of asymmetric drift in string theory, it appears, right? Where in fact, okay, yes, like from moment to moment, right, papers, if this is semantic space the papers are living in, they're kind of jagging around like this, right? Before they were kind of moving, but now it looks like they're slowing down, it's somehow stalling out, right? And so one way to say this is 5 years forward is 2 years back, meaning you have to wait 5 years into the future to get as much change, as much expectation violations as you did looking only 2 years into the past. So that's sort of the overall statistics of string theory, right, seen as a cultural process. Here's something that Alexander Barron, so Alexander's a graduate student at Indiana. We worked together on this problem. So now I'm just going to break this out paper by paper, right? So each dot here is a paper in the string theory archive, okay? On the x-axis is the surprise to the past, right? To what extent does the thing you've written, right, violate the expectations you have, right, given what's come before, right? So the further along the further along this axis you are, right, the more surprising you are, the more, let's say, novel or innovative you are compared to the past. On the y-axis is something like we sat for a second and then it suddenly struck us, right, that you can look not only at the surprise of something, at the surprise of your behavior given what's come before, but also the surprise of what will come next, right? So if you write something and it's really surprising what comes after you, right, your article is surprising compared to the future, sort of, you have to figure out what does that mean, right? Someone says, wow, like that's really surprising, given what people are going to be doing next, right? You don't look like the future, right? I mean, if somebody tells you that in your tenure review, that might not be a good sign, right? In some sense, surprise given the future is the extent to which you're forgotten. And so the obvious trend here, right? This is like data science 1.0, right? Is that there's a very, very strong covariance, right? The more surprising you are given the past, the more surprising you are given the future. Another way to put that is, maybe you call it like the first law of play, the first law of the unpredicted, right? What is new is quickly forgotten, right? What has been seen before won't be seen much again, right? So in this field, people are constantly producing innovation, right? They're constantly trying out new things. The extent to which the thing they're trying out is new is roughly the extent to which no one else is going to do it again, okay? It's just sort of sad. But of course, you look at this and the line is not perfect. So like take one of these pieces here. Take this article here, right? This article is very high on the x-axis, but if you look, it's kind of below the trend line, right? So it's surprising, right, given the past, but it's not as surprising given the future, right? It should be sort of way up here. It should be much more surprising given the future, and it's not. And in fact, if you look at these articles, right, you look at these things that fall sort of off this trend line down here, these turn out, of course, to be the citation classics, right? So this article, just picking this one at random, right? This one has 101 citations that puts it in for this field, it puts it in the top 5% of all articles in our data, right? I don't know what on earth it's about, but that's a separate story, okay? So another way to look at this is how much more surprising are these papers that get cited, or the papers that actually get picked up, right? And so here's, if you want to write a top-cited article, here's what you have to do, right? This is the difference in surprise between the top half and the bottom half, right? What you want to do is be surprising relative to the past and sort of roughly, like maybe like 2-3 years into the past. So if you're surprising, okay, given the past, then you will be less surprising given the future. You get that benefit. So basically break the rules from 3 years ago, right? And you'll reap the benefit a year into the future, right? That's sort of a kind of the risk reward to innovation. Okay? And those are drawn from there, right? And so another way to say this is, while it is true that most novelty is rejected, it is also the case that you might say the system honors the new. And this is, in some sense, the Calvinball problem, right? If there are no rules, if you're not trying to solve a problem, okay, if you're not all trying to get like the best high-temperature superconductor, right? If you're playing this game with all of your friends and colleagues all around the world, and you're inventing things like the Banach-Tarski paradox, right, or the multiverse in the case of string theory, right? How do you prevent the game from sort of going off the rails? So this is the Calvin and Hobbes joke, right? Calvin, if people have seen Calvin and Hobbes, like Calvin's this young boy. He has this friend, his imaginary friend, the tiger, and they play this game called Calvinball. And in Calvinball, the joke is that the rules advance just as fast as the moves in the game themselves, right? So every move in the game is also the creation of a new rule. And the joke, of course, is like, well, look, sooner or later, all games turn into Calvinball, right? How does string theory, if the job of string theory is not to describe the world, if it's not to solve some problem in the world, how does it stay on the rails? And of course, this is the fundamental problem. When you're on a bulletin board, you're talking, and you're not actually trying to solve a problem, how does that activity not simply become driven by the whims of everybody inside? This is a fundamental problem to understand when we're trying to figure out, okay, what are people doing when they play, right? And so we have some answer here, right, where, of course, string theory rejects most of what is new. It selectively picks some aspect of the new to become the driving force of what comes next, right? So those outliers, most of the really surprising bits of physics that people are writing get tossed out, but some small part of those surprising bits actually become the drivers of what comes next. So it's worth comparing string theory to another activity, similar activity. So we took a separate database. This is our second example of what's called fan fiction. Do people know fan fiction? People written fan fiction? So I'll explain fan fiction briefly. Josh is blushing. Fan fiction is when people take, they'll take something like Harry Potter, they'll take, I don't know, C.S. Lewis, they'll take Star Trek, they'll take, for example, this version of the Sherlock Holmes myth from BBC. And what they'll do is they'll write short stories that continue the characters, right? So in some sense, they've been given a kind of framework, they've been given characters, the characters have certain personalities. Hermione's always kind of like this, Harry's always like this, right? And they use those characters and put them into new situations and have them, play it out, right? So they write short stories. These short stories are often, so the sociology of fan fiction is fascinating. It's mostly written by women. It often has a sexual aspect to it, an erotic aspect to it. Yiji, who's somewhat of an expert on fan fiction, we worked together on this problem. So she downloaded, she scraped one of the major fan fiction websites called Archive of Our Own, AO3. You get a sense, Archive of Our Own, right? There's a sort of countercultural aspect to fan fiction. And she said, okay, I have 90,000 articles. I have 90,000 short stories in my database. And I said, well, that's amazing. She says, that's for the archive. She says, no, that's just for that particular Sherlock. So there's over 90,000 short stories that have been written extending the universe of that particular BBC version of Sherlock, right? Almost all of them written by, they're not written by professors of literature, right? The amount of human creativity hidden in something like fan fiction is enormous. Like, this is like the dark matter of play, right? We're very aware of the sort of elite production of novelty, but in fact, hidden in certainly hidden on the internet, are amazing features like this, right? So 90,000 short stories just on this one archive. I won't go too much into it, but I will tell you one of the findings we have here, right, which is fan fiction versus string theory. One of the things I showed you is that in string theory, unusually novel articles tend to be given high citations. Well, right, put it this way, sorry. The articles that have very high citations, the ones that are rewarded by the community, are preferentially drawn from the unusually novel subset of articles in the database as a whole. This turns out to be the opposite case in fan fiction. So in fan fiction, we don't have citations, but we do have like likes. We have ratings, what are called kudos, right? So in the case of fan fiction, it turns out, in fact, the community is somewhat conservative, right? To write, if your goal is, and you can sort of expend all the resources you want to, if your goal is to write a piece of fan fiction that the community will like and read and share with each other, then what you ought to do is write an article that looks actually very similar to the median article, which is the opposite of the game in string theory. In string theory, if you're really ambitious, what you try and do is you write something on the periphery. Okay? So we can see a little bit here, right? In this case, kudos declines with Kullback-Leibler divergence. Okay? And that's in contradiction, or in contrast, to what happens on the physics archive. An intermediate example, and this is work with Jenny Huang, comes from a study of lyric poetry in Poetry Magazine, it turns out. Poetry Magazine is, in many ways, like the sort of elite repository of Anglo-American poetry. It's published out of Chicago, but they basically publish all of the major works of literature in the 20th century that you know. We don't have, I won't have time to go in depth into this one. One thing I can tell you, so Jenny did essentially the same thing that we did with string theory and the same thing that we did in the case of fan fiction, was say, look, in this case, it's about 20,000 poems that we're able to identify in Poetry Magazine. Our big question is, what defines whether or not they make it into the anthologies? That's our sort of record of cultural success, right? And in fact, in that case, we see this big switch. So if we look at innovation over time, this is the average Kullback-Leibler divergence over time. The early, actually, sorry, this is similarity, so you should flip this mentally, right? The early poems that get canonized, these little red dots here, right? And this is people like Pound and Eliot, right? These poems here make it into the anthology. They tend to be less similar to the past, right? So this is like the string theory era of poetry, okay? There's something crazy happens in the 1960s, right? There's an enormous sort of burst of innovation. So in fact, all poems are less similar to the past. In the second half of the 20th century, it flips from being string theory to being novelty seeking to fan fiction being novelty avoidance. So in fact, in this case here, we can see a switch in the dynamics of the system. Okay? We've been able to do a lot of studies here of how, in particular poems either achieve or do not achieve influence over the past and, of course, the future, the extent to which they imitate the past or violate the expectations of the past. But I will skip over this, since I would like us to get to the second part of some speculative work we have on conflict. So here's the summary we have so far, right? On the one hand, right, we have studies of how systems either accept or reject novelty, how they either copy the patterns of the past or reject the patterns of the past, and the way in which the social community either validates or rejects that choice. We might talk about the management and dynamics of novelties. But one of the questions we have is, okay, we know what happens, right? Or rather, we can look at what happens when somebody injects something novel into the system, right? But our converse question is, okay, where does that novelty come from to begin with? What triggers, for example, that burst of innovation in the 1960s in Poetry Magazine? What drives a scientist to write an unusually new kind of paper? And of course, in fan fiction, what drives a fan fiction writer to violate the expectations of her audience? Okay. So if you ask academics, right, like where does novelty come from? Where does innovation come from? Where does truly exciting stuff come from? They tend to have this very kind of cooperative view of the way the world works, right? You get together, you get all the smart people you can together, right, in some conference, and your interests are all aligned, and you're all friends, and you talk it out, and then you invent quantum mechanics. This turns out not to be how science works, and we know this because, like, we all hate peer review, right? We think peer review is like the worst thing ever, and we're constantly fighting with each other. This is the paper I wrote. I will put this on the screen. I suppose I really shouldn't, but it's okay. This is a paper I wrote with Chanda Presker-Weinstein, who's now a professor at the University of Washington. But we wrote this paper together, and here is our peer review, which is the most vicious peer review of all time, at least that I've gotten. This manuscript in several instances provides observations that are better suited for a coffee break. I could give an ultra-long list of examples. Anyway, one of the features of successful systems, right, it turns out, is not just getting people together in a room and being friendly, but also setting up institutions that allow us to productively fight with each other. Like the rules, like what does peer review do, right? It enables an anonymous person, right, to criticize you, right? This is not like the most friendly thing in the world, right? Like a friendship where, like, if a friend sends you an anonymous message saying like you smell, like that might be helpful, but that's not how friendship works, right? What we do is we create constantly in any field, and this is something we can talk about in terms of the court system, or we can talk about in terms of the free market, but even in something that we seem to think of as this highly collaborative environment is actually riven by conflict and structured. Okay. There are rules, but at the same time, we provide possibilities for people to, in some sense, harm each other, right? And we protect them, in fact, from that harm. It was actually, so the story on this one, we can talk about it afterwards. So this one, we actually were able to figure out who wrote this referee report, and we later became friends, but that's a whole separate story. It did indeed, of course, kill the article completely. So here's my example. We're unable, if anyone wants to WikiLeaks, like a journal's peer review system, I would be really pleased. But in the absence of WikiLeaks for physical review, we have to look at conflict in more open systems. So that's the final thing I'll talk about here in the few minutes that remain. And this is, of course, Wikipedia. Wikipedia, because it's so open, allows us to look at how the creation of new forms of articles, the change in an article over time, its evolution over time, how that coexists with the conflict between the users, right? So Wikipedia, who here has edited Wikipedia? Can you raise your hand? Okay. Who here has read Wikipedia? Like if you haven't, I don't believe you don't raising your hand, right? So everyone uses it. The joke is Wikipedia is used for practically everything. It's cited in court decisions, at least in the United States and probably here. Your doctor will look at Wikipedia in order to decide how to treat you at this point. Medical students revise for it. It's a disaster. If you look at what the purpose of Wikipedia is, right? Wikipedia's purpose is to benefit readers by acting as an encyclopedia, a comprehensive written compendium that contains information on all branches of knowledge. So, like, I don't know what that means. It's pretty much something like this, right? We have no one really knows what Wikipedia is for. There's huge debates. It seems like this does not in any way define what Wikipedia is for. And so one example is, of course, the great battle between the deletionists and the inclusionists on Wikipedia, right? So some people believe that Wikipedia should have an entry for every single thing in the universe. Like there should be an entry for the Enigma room. There should be an entry for like the collection of chairs in the Enigma room. Like if there's a particularly useful chair, that should have its own entry. These are the inclusionists. The deletionists say like, no, there's got to be a cutoff. So like not the Enigma room, but maybe the Alan Turing Institute gets a Wikipedia page. This is a conflict that appears in all the languages. In the Russian case, they actually formed two political parties within the system, the deletionists and the inclusionists. And they actually had, basically that's the Republicans and Democrats for at least the Russian language version. The most edited article on Wikipedia, I make people guess this. What is, in the English language, what is the most edited article on Wikipedia?
Wikipedia?
Close, that's in top 10. You know these things, haha, of course. But no, it's close. There is, so the article on Wikipedia itself is highly edited. Any other guesses? No, but probably high. Not in the top 40 that I remember. No.
The main page.
So excluding the main page. 9/11 is, I can't remember if it's in the top 40, but you're getting close, right? So Jesus, that's the closest guess so far. It's actually George W. Bush. In some sense, right? And the other joke is, don't you miss this guy? But Bush, so one of the reasons Bush is so highly edited, of course, is that his highly controversial presidency that lasted 8 years also coincided with the growth of Wikipedia itself. So if you look at the history of edits on Wikipedia, and you look at the history of edits on this page, you can also work out what the hell is going on, right? People are trying to figure out what Wikipedia is for. So there's 45, at least when I started this, there were 44,000 edits to the George Bush page, and there's constantly being added, so I get to do I can test my theories out of sample. Let's do the same thing we did for string theory, right? So let's look at the edits to the page, right? So there's 45,000 edits, so each page is a version that differs from the ones that came before. And so I can plot, for example, the Kullback-Leibler Divergence, right? How surprising is the current page given the one previous? And it looks like this mess here, right? So it's just this kind of, right? Make it a little bit easier, and we say, okay, how surprising is the current page given the 1,000 just previous? And now we start to see a bit more structure, right? You can see like it sort of idles along, people are making edits, and occasionally it's like pow, right? Some big edit happens to the page, right? That really strongly deviates from what's come before, right? And that edit kind of, that page then becomes more and more normal as of course this past history gets incorporated into the comparison. And so, I mean, okay, if you're a philosopher of science, you think about these kind of big revolutions, right? These kind of paradigm shifts and what people think the page is about. These innovation bursts are real, right? If you just look sort of on one side or the other of one of those bursts there, right? You see that burst, pow, right? You look at the page right before the burst and the page right after the burst, that first one that you see. I won't show you the entire article, it's very long, but if you compare them, here's the table of contents at point A, here's the table of contents at point B. The major change here, most things kind of carry over pretty much the same, but the major change is this thing here, where people have decided that Wikipedia is now going to include information about the scandals surrounding the George Bush presidency. Okay. So in some sense, that burst, right, that we can see in the Kullback-Leibler divergence corresponds to a semantic shift in how people are viewing the purpose of the page, and that semantic shift sticks around for a long time. Okay. So we can measure the introduction of innovation to the system, right? These are sort of like these big changes, right? These great deviations from what's come before. But we can also ask, okay, what's the relationship between those bursts, between the introduction of this novelty, right? And in particular, in the conflict that happens on the page. And so I'll just give you an example of how we can track conflict in Wikipedia. This is a very simple way to do it, and it's what we call the revert. So here's an example. I'll show you an example of conflict on Wikipedia. Here's a page. This is the Israeli-Palestinian page. Right? We know all of the edits made to this page, and so we can look at the history, what's called the history page, associated with this. So I've just taken a random clip here, so you read from here going upwards, right? So people are making edits, and one of the things you can see, right, so at the bottom of the page here, this user like Schmooth, on the 28th of November, 2014, Schmooth, right, makes an edit to the page. And we don't quite know what Schmooth has done, but he actually says what he's done in the little comment there. He says, look, I added a small paragraph explaining what the conflict is actually about, as the current article fails in this most basic of tasks, right? So that happens 3 minutes before midnight GMT, right? At sort of 3 minutes later at midnight GMT, the usual Daniel J. Levitt comes along and he says, like, no. Like, this is a complicated thing. Like, you just showed up. You have no idea what you're doing. And what Levitt does is he RVs. He reverts. And that's like hitting Control-Z. So he undoes the edit. So that little tag there, right, where I've highlighted here, what he's done is essentially undone the edit that Schmooth did. He doesn't change it, he doesn't alter it, he doesn't try to fix it, he just says no, he hits Control-Z. And in fact, this actually happens again later. So, okay, something comes along, like this user here comes along on the 27th of December, makes an edit. He says, look, I've done some fixes here, and I've removed some unclear words, okay? And then in fact, about a day later, another user shows up and he says, I've RV'd, I've reverted, this is like nerd speak for revert, I've RV'd, unsourced, POV pushing, so clearly these people are in conflict. So reverts are really nice because they're generally associated with norm violations. Reverts are kind of the sort of nuclear weapon, right, or like the tactical nuclear strike in Wikipedia. People don't like them. When they happen, they tend to be associated with conflict. Okay. So what we can do is we can take a page and we can decompose it into edits that are either creative, we'll call those Cs, or reverts. And so this is actually the binary time series for the George Bush page. And what you can see is that actually it only takes 3 edits until somebody does a revert, right? So that's like in 2001. Thank you very much. So we can ask a very simple question, and perhaps this is where I'll end, right? What is the relationship between distance to the revert, right, distance to these flashpoints, and innovation, Kullback-Leibler distance? Okay? And when you look at this page, right, when you look at this particular page, and this pattern seems to hold, it appears that conflict suppresses innovation, right? The further you are away from a revert, the further you are away from a flashpoint, right, the more surprising the edits tend to be. When people are fighting, they're not innovating, right? In the aggregate, conflict appears to be associated with the suppression of innovation. Now, this turns out not to be the final story, right? Because if you go back to that time series, and we were in fact able to do some machine learning on this, what you find is there's actually 2 distinct kinds of patterns associated with how people argue. We built a simple Markov chain model of this, hidden Markov model of this, and what you find across many, many pages is in fact this 2-phase form of conflict. Sometimes you're in one conflict pattern, sometimes you're in the other. And you flip back and forth between these. There's many differences between the 2 kinds of conflict. We call them type 1 and type 2, right? There's many distinct forms of patterns associated with them. Fundamentally, type 1 conflict is slow. It's lower conflict on average. There's fewer reverts. But when there are reverts, the reverts tend to be tit for tat. Type 2 is much faster. if we look at the innovation rate for type 1 conflict, it's much, much higher than the innovation rate for type 2 conflict. And in fact, now we understand that type 1, we might call it the innovation mode for the system. And now when you're in that type 1 conflict, the result goes the other direction. This is what we call in economics the ecological fallacy. In the aggregate, conflict is bad for innovation. But in fact, when you're in type 1 conflict, it turns out that it's good. Now, if you're in the right kind of conflict, innovation is actually higher the closer you are to a flashpoint. So you've been very gracious. I'm going to skip my sort of details on why you ought to believe this. And I'll just give you two open questions for this talk. The first question is, what tilts systems between novelty seeking and novelty avoidant? Right? String theory seeks novelty. Right? Fan fiction, at least as far as we understand it, actually avoids novelty. It tries to replicate the patterns that other users have created. Right? Lyric poetry is somewhere in between. The second question is, what patterns, what institutions, what events nurture and promote innovation? I've given you some sense that, in fact, innovation doesn't come from nowhere. It's not just that these geniuses come in and change everything. But they may be selectively nurtured by other aspects of the system. And surprisingly, in some sense, they may be nurtured in part by conflict. When somebody does something that is truly new, it may engender conflict. And conversely, conflict may be particularly productive of the new. So you've been very gracious, and especially since I've gone 2 minutes over. So thank you very much.